There are a number of other types of errors that can ultimately affect your measurements in a mechatronic system. So the first one we'll talk about is linearity error. And when we were calibrating our sensor, remember we generally provided a linear fit to that, where we have our kind of model of our sensor is A0 plus A1x, basically just a linear line that I would draw on this x versus, or y of x versus x curve. So in this case, that might look something like this. Now the problem in this case is that the model might actually be slightly different. So I might, have some in this case it's a slightly complex contrived curve, but this might be the kind of real fit to my sensor data that I'll call just some function of x here. Right, so the linear fit is really only an approximation, and as a result I'm going to have some error from that. So that linearity error, I'm going to call E linearity, is going to be a function of whatever input I have. Obviously it's going to be different at different points, and that's going to be y linear minus the true y of x. And that would of course be measured in whatever output units y of x is. So maybe it's a force sensor that has a resistive output. So x is newtons and y would be ohms. So my error in this case would be in ohms. But one thing we often try to do in terms of error is frame everything within the same context. In this case, frame everything relative to the output range of my sensor. So if I define this distance right here as the output range, I'm going to call that R0, and I look for the maximum linearity error that I would have in here. So maybe somewhere around here, that distance right there, I'm going to call E linearity max. And then I'll have a percent E, and I'm just going to shorten it to L here. Max is equal to that maximum linearity error in this case, whatever the output units are, normalized by the output range, and then of course times 100 to put it in percent. Right, so this is given effectively percent full scale output range is something that you might often see in a data sheet. One thing you occasionally see when you're calibrating a sensor is that as you provide an increasing independent variable to it, so maybe that's a force or something like that, I might get a curve that looks something like this. So I'm providing an increasing value of x here and measuring y of x. Now, when I start decreasing x, what I sometimes see is that I get a different curve here. Right, so now the return is looking different than the loading phase in this case. And this is what we call hysteresis in the sensor. And hysteresis really comes down to memory. So it matters if I'm increasing my load or decreasing my load. That's what we mean by memory. And it's often due to things like energy losses, whether they're thermal in a polymer or acoustic or some other fashion of energy loss is going to lead to this hysteretic behavior. Okay, so the problem if I have a sensor that has a fair amount of hysteresis in it, if I'm trying to make a measurement and I'm applying x, some known x here, then I could have two different outputs depending on what my previous input was into the sensor. If it was down here and I moved up a little bit, or if it was up here and I moved down a little bit. Right? So I have two different outputs, and I'm going to call that y low and y high here based on that single x input. So that right there is the hysteresis error. So once again, if I try to measure this relative to the output range to get a percent full scale operating range, I'm going to get a percent of my hysteresis error that I'm going to designate EH max, and that's going to be the max point of that y high minus y low. So I'm going to add a max out here, once again normalized by that output range, and times 100 to get it in percent. Another type of error that is not uncommon in a data sheet would be sensitivity error. So I might have some typical sensitivity in my sensor. So let's call that K typical. And I might have some bounds on that. So I might have a lower bound where I have some minimum sensitivity, and of course I might similarly have some upper bound where I would have a maximum sensitivity. One way to quantify this sensitivity error, in addition to using the output range that we've used before, is also using input range right here. So maybe this is my output range and my input range. And in this case, I'd look at my K max minus my K min. That would have units of output divided by input units, and multiply that by Ri over R naught, and that by 100 once again to get my sensitivity error, my maximum sensitivity error in percent. And so based on the possible spreads of this sensitivity, if I have a fairly high spread there, I'll end up with a fairly high sensitivity, maximum sensitivity error. If this is very tight around this kind of K-typical value, I'll end up with a smaller sensitivity error. And of course I have lots of other different kinds of errors that I might encounter in my sensor. Those are just 3 that are fairly typical. And if I'm trying to understand the overall quality of the data that I might get in my measurement, I want to look at the total error. So the total error in this case, we're going to use the root mean square. So I'm going to look at the square root of the sum of all of those errors squared. So I equals 0 to however many errors I want to kind of throw into this particular measurement. And of course, if I'm doing this, I want to make sure all of them are non-dimensional or have at least the same units, maybe output units. But I need to make sure everything has the same units in order to throw everything into this total error metric. So as a quick example, if I have a linearity error given in full scale range of, say, 2%, I have a hysteresis error of something on the range of 1%, and those are the only ones I want to consider. What is my total error in this case? It's going to be the square root of 0.02, that 2% squared, plus 0.01 squared, or about 2.2% total error here. So these will give me some value, some idea of the spread of data that I might expect during my measurement, and the total accuracy of my measurement with all of these errors.